Alright, here's lesson 5 on writing a function rule. Many real-world functions can be represented by equations, and you can use those equations to find solutions to the given real-world problem. So what we have to figure out is how to write these function rules. How do we turn a word problem into these function rules? Remember, a function rule is just an equation involving two variables. It always has our input and our output. The input is almost always what we're going to be plugging into the equation part. The output is almost always going to be what it equals in the end. So that's how you can kind of keep things straight. It does not matter what we define our input or output to be, but they are both going to be variables. So you'll see in many of these cases we will define them not to be x and y today, but we'll define them to be different letters that are going to represent things in the word problem. So let's see this word problem here. You can estimate the temperature by counting the number of chirps of the snowy tree cricket. The outside temperature is about 40 degrees Fahrenheit, more than 1/4 the number of chirps the cricket makes in 1 minute. So what is a function rule that represents the situation? Now, just like in the last unit when we were talking about word problems and the different strategies to go through and to be kind of running through a checklist in your head of what I'm doing, we're going to do the same kind of thing today here. So what we want to do first is try and relate this information, sift out the important pieces from this word problem and try and put it together in a sentence that we can then make some sense of. So the first thing we want to kind of recognize here is what is the situation we're trying to represent? And I think it's going to be the temperature outside. So let's see. Yeah, the temperature is 40 degrees Fahrenheit, more than 1/4 of the chirps in 1 minute. These are the important words here. So let's see. Temperature, the temperature is 40 degrees Fahrenheit, more than 1/4 of the chirps in 1 minute. So is usually represents equals. More than is going to be plus. So we're going to have 40 degrees Fahrenheit plus 1/4 of the chirps in 1 minute. Of means multiply. So 1/4 times the number of chirps in 1 minute. Okay, we see that you can estimate the temperature up here by counting the number of chirps of the snowy tree cricket. The outside temperature is 40 degrees Fahrenheit, more than 1/4 the number of chirps the cricket makes in 1 minute. Okay, that's where we got all this information from. Let's now take a look at when we define our variables. So we're going to remember we're going to have two variables now. One of them is going to be our output. It's going to be kind of the y value that we've been talking about, and it's going to be what's on this side of the equation here. So the temperature. Okay, so let's define the temperature to be maybe T. So let T be the temperature, and we're going to need a variable for the number of chirps in 1 minute. So what would be a good thing to use there? A lot of times whenever we have the number of, we'll use the letter n. So let n be the number of chirps in 1 minute. Okay, so now I have two variables. I have my input and my output. I know that my output is going to end up being this temperature. This is going to be my output. And this is going to be my input. So this was kind of like my x value, and this was kind of like my y value. All right, so now what we want to do is we want to turn this into an equation. So it's going to say T is going to equal, so we're going up to this relate part up here. So the temperature equals, we're going to need that 40 degrees Fahrenheit, so 40 degrees more than, so plus, a quarter of the chirps in 1 minute. So 1/4 of means to multiply. So let me write in that multiply. I can use parentheses. Times n is the number of chirps in a minute. Okay. If I wanted to solve for this, well, I can't really solve anything. I have two variables, so I would need to know some more information. Like the cricket chirped 87 times. Then I would know what the temperature was. I would plug in 87 for n, and that would be able to determine what t was. Okay, so you want to follow these steps when you're creating a function rule. You want to first try to relate the information. Definitely define your variables. Like this is an absolute must. You have to be defining your variables. And then you're going to use that information to try and write the equation. Now remember, I'm going to ask you, if you're having trouble doing any of these, writing these equations, I'm going to ask to see where's your, where did you pull the information out from? I want to see what you're relating, and I definitely want to see how you're defining your variables. Okay, because without those two steps, it's really going to be quite difficult to write any kind of these function rules. All right, so let's evaluate a function rule. First, we're going to have to come up with the rule, and then we're going to actually evaluate it. Remember, evaluating now is going to mean, it's kind of means solve. So we're going to solve for some sort of variable. We're going to plug stuff in and try to figure out some real-world scenario here. So a concert seating plan is shown to the right. Orchestra seating is all sold out for a specific concert. The total revenue from the ticket sales will depend on the number of general seating tickets sold. So let's write a function rule to represent the situation. And then we want to know what is the maximum possible total revenue. Total revenue is all the money that you are getting in. So whenever you see revenue, it's the money that you are earning, the money that you're getting. Okay, first you see we're doing the same thing again. We're going to relate. So what is going on in this question? Well, we have the total revenue. We know that that's what we're going to be looking for. Is the general seating revenue, so whatever you are making from the general seating, plus the reserve seating revenue. Okay, and that makes sense, right? If you think about it, all of the money that we're going to make is going to be based off of how much I make from the general seating and how much I make from the reserve seating. The reserved seating is the orchestra seating here in this case. So let's define our variables. Okay, so the total revenue, that's something we don't know. That's going to be our output. That's what we're going to be figuring out. That's what this whole function is going to be doing for us. It's going to be figuring out the total revenue. So let's let R be the total revenue. And then what else do we not know in this? Well, let's see, the total revenue from ticket sales will depend. Notice that's another keyword there, depend. Okay. If something depends, then that is the dependent variable. Okay, the total revenue depends on something. So that means that is my output. Okay, it depends on what? Well, it depends on the number of general seating tickets sold. So that's the other variable, the number of general seating tickets sold. That's what's going to change. As that changes, the total revenue will also change. So let's see. Let N be the number of general seating tickets sold. Okay, so let's create an equation here, a function rule. We're going to have the total revenue, so R is going to equal, total revenue is, the general seating revenue. Well, how do I know what the general seating revenue is? It's N for the number of general seating tickets sold. So that's the number sold times how much they cost. So the general seating over here costs $10 per ticket. So it's going to be n times 10 plus the reserve seating revenue. Now this question already tells me that that's sold out. The orchestra seating is sold out. That is the orchestra seating up here. So if it's sold out, then that means I got $25 for every ticket. And how many tickets were there? Well, there was 10 rows with 12 seats. So 10 times 12 is 120. And 120 times 25 is 3,000. So let's write it like this. It is the 10 rows times the 12 seats times $25. That's going to end up being 3,000. All right, so let's kind of make this look nicer here. So the revenue is going to equal 10n, we should put the constant first, plus 10 times 12 times 25, that's going to be 3,000. All right, so let's see, what is the maximum? So here's our function rule. We did this first part, write a function rule to represent the situation. Check. What is the maximum possible total revenue? Well, the total revenue would be if every single seat in this whole place was sold out. Okay, so I already know these are all of the orchestra seats or the reserve seating. That's all the money I can make off of those. So what is the total I can make off of the general seating? Well, I have 30 rows and 16 seats in every row. So the number n, the number of tickets that I can sell is going to be 30 times 16 and then times that $10. So the revenue is going to be 10 times this 30 times 16 plus 3,000. And the 30 times 16 is going to be 480. So R equals 10 times 480 plus 3,000. So R equals 4,800 plus 3,000. So R equals $7,800. And that would be the maximum possible revenue ticket sales. And again, since we have our let statement up here, let R be the total revenue. So this tells me the total revenue is $7,800 if we sold out this venue. Okay, so up until this point, up until this point where we created our function rule, that was just like what we did on the previous slide. And then from here down, this was us evaluating our function rule given some sort of stipulation. So write a function rule to represent the situation, then what is the maximum possible total revenue? So that last part was that. What is the maximum possible total revenue? We had to plug in something for our independent variable, which was the number of general seating tickets sold, N, and that gave us what R was in that given situation. Alright, so how about nonlinear function rules? So writing a function rule for the area of a rectangle whose length is 5 feet more than its width. What is the area of the rectangle when its width is 9 feet? Alright, so these are a little bit more difficult, and one of the best ways to evaluate these types of nonlinear functions, and I know this is nonlinear because this is dealing with area. An area is that's a square unit. So I'm going to be looking at a quadratic or an x squared type of thing here. So a type of function rule here. So let's see. In the first step, what we're going to want to do is let's represent the relationship using a table or a picture or some sort of way, in some sort of graphic organizer way, to take this information and make some sense of it. So what is it we're even talking about here? Write a function rule for the area of a rectangle. Right, let's start with that. The area of a rectangle. Okay, so why don't we take and create a picture like a rectangle, and we'll label some sides, and we'll try and remember and recall exactly what the area of a rectangle is. So you draw a rectangle. We say the area is the length times the width. We label the two sides, the length and the width. And now we have something to start applying our information to. All right, step 2. We're going to rework the model that we just created to show the length is 5 more than the width in this case. So part 2 here, let's see, the area of a rectangle whose length is 5 feet more than its width. So that means we have the width, and then the length would be the width plus 5. So instead of having the length now, we have the width. And everywhere that we had the length before, we're going to replace that with the width plus 5, w plus 5. Because the length is 5 feet more than the width. Okay, so if you want to, you can write something like the length is 5 more than the width. So notice the length equals this, which means I can substitute it in. So wherever I saw an L before, now I'm going to put this W plus 5. All right, now finally, what are we going to do? Well, we're going to see what this question is asking. What is the area of the rectangle when its width is 9 feet? Okay, let's first write our function rule, and then this is getting specific. It's telling us what to plug in for the width. The width is going to be my independent variable. The area is going to depend on whatever I plug in for the width. So the area is the dependent variable here. Okay, so let's see what happens. We're going to want to use the model to write the function rule and then make any necessary substitutions and solve it. Okay, so we're going to have the area, just like up above, equals this width times, or width plus 5 times width, or you can relook at that and say width times width plus 5. I like to have the single kind of variable out front. It just makes it a little bit easier to see. This would be distribution if you want to. You could have W times W. Remember, that's not W, or that's not 2W, that is W squared. Okay, if you wanted to distribute this, you could. You could say W times W is W squared, and W times 5 is 5W. In this case, I'm not going to. I'm going to leave it like this. And we are now going to make the appropriate substitution. Notice it tells me the width is 9 feet. So you could say the width equals 9. So everywhere where I saw a W, I'm going to now put the number 9. Okay, be careful here. You can do this two ways. I think the easier way is to simplify the parentheses and say 9 plus 5 is 14. So I'd have the area equals 9 times 14. And you grab your calculator and you determine the area of the rectangle is 126 when its width is 9 feet. All right, let's see what you know. We want you to write a function rule to represent the following situation down here. Okay, the situation is this. The total cost C for P pounds of copper if each pound costs $3.57. Okay, just to make sure you are on the right track here, the total cost, C, so it's defining your variable for you. This is going to be your output. For P pounds of copper, this P is going to be your input. Okay, this is going to be like your x value, and this is going to be like your y value. All right, good luck, have fun, and I will see you next class.